Welcome to this quantum security and defense presentation. Multipartite entanglement distribution in bell pair networks without Steiner trees and with reduced gate cost. And thank you for being a valued member of our community. Siddardha Chelluri is a PhD student in Johannes Gutenberg University in Mainz. His research focuses on quantum communications and quantum error correction, with a particular focus on quantum repeaters and quantum networks.
Thank you very much for the opportunity, even though it's short. So it was nice for me also to present the work that is recently out in the archive. So yeah, so the title might be a little bit too long or scary, but don't worry, this doesn't really matter. We will go into it in a more easier way. So this is done in collaboration actually with Sumit Khatri, now who is a professor at Virginia Tech in the US. And so the findings of this paper, like I'm basically presenting the contents from my paper, and this was like in the archive recently. So you can also check out in the archive for the things. So a little motivation. I think like we are all enough motivated to work in the quantum industry, I hope. So we don't need a lot of motivation, but yeah, this is basically the idea that you have like a lot of things that could transform with the quantum technologies like cryptography and optimization problems, machine learning, quantum simulation. There are like a lot of applications, but for most of this quantum applications, you need this multipartite entanglement. And also for some of them, you also need multipartite entanglement across distant nodes. That means like not only locally that you have some qubits which are entangled, but also that are far away, especially for cryptography, quantum communication tasks, and so on. So this is the central point of the problem. So now the question is that how do we create a GHZ state among selected nodes from the given network topology of bell pairs using only LOCC? So I would explain this. So like now we have like a network. This is like a quantum network. So some bunch of cities connected by some optical fiber cables, let's say, and then you want to do like this quantum like what you want to do is like basically like able to distribute the entanglement in such a way that like everybody can securely communicate with each other, and this could be done by generating a GHZ state. So if you have such a state, if you have such a connection, then everybody can like connect with each other, can like decipher like distill a security key and so on. It's basically like this BB84 protocol, not just between Alice and Bob, but also between several other parties. So that's basically the setup. And here I want to explain few things. So in quantum information, like we can also show the quantum states by graph. So for example, the state that you see, which is like this star shaped, this is like the GHZ state. So every node here belongs to a qubit. And then if there is an edge that is connecting, that means that there is a CZ gate between them. So that's how you can see like this graph. So now so you start with something like this, you have network some connection. For example, 3 is not directly connected to 9, but you want to make these connections change in such a way that you have this scenario which represents this GHZ state so that you can communicate. So that's basically the question that we are trying to answer. So this question is not new, and therefore I want to show you a little bit like the known protocols. There are already like a couple of protocols which are in there. And then, but there are some problems in the protocol which I would try to address and then explain our protocol and some results that we obtained from this. And there is also some things for these new ideas and directions, possible directions, but maybe I would not reach here in time.
Watch the full presentation and other expert presentations online. Search for Quantum Security Defense.